Okay, so you know how sometimes you just get in the mood to like really learn something?
Yeah.
I mean, like something seriously complex?
Uh-huh.
That's what we're doing today. It's like we're scratching that itch,
Yeah, right.
that deep dive itch, and we're diving deep into the 7 Millennium Problems.
Which are basically like the Mount Everest of math problems.
Exactly. Unsolved, super challenging. I mean, we're talking about stuff that stumped the greatest mathematical minds for years, decades even.
Hmm.
We've got research papers, articles, all kinds of intense stuff to dig through.
Yeah, and the thing is, these aren't just like these head scratchers for, like mathematicians and their ivory towers.
Yeah,
The cool thing is that these problems could actually have like real world implications for things like cryptography,
right.
physics, even like how we understand the structure of the universe.
Okay, so before we like completely nerd out,
It,
let's talk about what's at stake here.
okay.
Because we're not just talking about bragging rights.
No, no, no.
We're talking about a $1 million prize
Yes,
for ETH problem solved.
that's right. Put up by the Clay Mathematics Institute. That's how big a deal these problems are.
That's right. So like solving one of these things, I mean, that's not just like a gold star on your math test.
It would be huge. It would be like a monumental leap forward, not just in mathematics, but potentially across, like multiple scientific disciplines.
Okay, let's jump into the first one. And full disclosure, this one always kind of makes my brain do a backflip.
Yeah.
We're talking about P versus NP.
Okay.
So in like super simplified terms, what's the core concept here?
Okay, so imagine this. You have a problem, right? And you can easily check if a solution to that problem is correct.
Okay.
Does that automatically mean that finding the solution in the first place is also easy?
Okay. So like with a Sudoku puzzle,
Mm.
it's easy to check if it's solved correctly.
Right.
But actually solving it, that
Yeah.
can take forever.
Yeah, exactly. So P versus NP is asking, are there problems out there where verification is a piece of cake?
Uh-huh.
But finding the solution is incredibly complex.
Okay, so what are the like potential implications of this? Because this sounds like it
Yeah.
could be kind of a big deal.
Oh, it's a huge deal. Like imagine, what if cracking seemingly unbreakable codes
Yeah,
suddenly became simple?
right.
Or what if we could optimize incredibly complex systems,
Like what?
like global logistics networks,
Uh-huh.
financial markets, and we could do it with ease?
That's a lot to wrap my head around. I mean, it sounds like the consequences are huge,
Yeah.
both positive and maybe, I don't know, a little unsettling.
Absolutely. I mean, that's why P versus NP is considered a holy grail of computer science. The answer could revolutionize our technological capabilities in ways we can barely even fathom. It's crazy to think about.
Yeah, it is. Okay, let's move on to something that also has like huge implications.
Right.
We're talking about the Riemann hypothesis.
Okay.
Now, this one is all about prime numbers.
Yeah.
And I remember from school that prime numbers are those numbers that are only divisible by one and themselves.
Right.
But can you remind me, like, why are they so important?
Okay, so prime numbers, they're like the building blocks of all other numbers, and they have this strange, almost musical distribution pattern. It's really weird.
Right.
So the Riemann hypothesis, what it does is it proposes a specific mathematical function that predicts this pattern perfectly. Like imagine uncovering a secret melody that's embedded within these seemingly random numbers.
Okay, I'm with you on the melody analogy. But help me connect the dots here. How does this melody of prime numbers connect to, say, my online security?
Oh, it's very connected. A lot of the encryption methods we use today for everything from online banking to secure messaging rely heavily on prime numbers. The difficulty of factoring large numbers into their prime components is actually what makes those encryption methods secure. It's really fascinating when you think about it.
So if the Riemann hypothesis is proven true, and we like fully understand this prime number melody, could that like throw a wrench in our current encryption methods?
It's a possibility. A deep understanding of the distribution of prime numbers could lead to more efficient ways of factoring large numbers, which, yeah, could potentially undermine the security of some encryption algorithms. But on the flip side, it could also help us create even stronger encryption methods, making our digital lives even more secure.
It's amazing to think that like these abstract mathematical concepts have such a tangible effect on our daily lives.
I know. It really is. People think of math as this like separate abstract field, but it's so integrated with our world.
Right. Let's move on to a question that's fundamental to, well, literally everything. Why does anything have math at all? Enter the Yang-Mills and mass problem.
Right. Now this one really takes us deep into the realm of quantum physics and particle physics. So Yang-Mills theory, it describes the fundamental forces that govern how particles interact. But the problem lies in connecting this theory to the property of mass. Why do some particles, like electrons, have mass,
Ah.
while others, like photons, don't? It's a really strange thing to think about.
So it's like we're trying to figure out the source code for why matter behaves the way it does.
Exactly. Like if we could solve this Millennium Problem, it'd be like finding the missing link between quantum mechanics and our understanding of the universe at its most fundamental level.
Wow.
I mean, think about it. It could help us understand why the universe exists as we experience it.
Right.
Why stars form, why planets coalesce, ultimately why we're even here having this conversation.
Okay, I need a minute to process that one. Let's come back down to Earth for a second and talk about the Navier-Stokes equations. Now, this one, if I'm understanding correctly, has to do with how fluids move, which sounds pretty straightforward.
Right.
We see fluids moving all the time.
Well, the basic concept might seem simple. We're talking about the flow of liquids and gases, but the Navier-Stokes equations, which are used to describe this motion, they're notoriously difficult to solve.
Really?
Yeah, think about it. We rely on understanding fluid dynamics for a ton of stuff.
Like what?
Weather forecasting, designing airplanes, modeling ocean currents. We encounter this stuff all the time.
So our ability to, like, predict the weather accurately or design more efficient airplanes, it hinges on us understanding these equations.
Exactly. The problem is, we haven't been able to find general solutions to the Navier-Stokes equations. We can approximate solutions for specific situations, but a complete understanding, it's still elusive.
So what could happen if we, like, crack the code on this one? What kind of breakthroughs could we see?
Oh man, imagine weather forecasts that are accurate weeks or even months in advance, or airplanes designed with like unparalleled aerodynamic efficiency, leading to faster travel times and reduced fuel consumption. We might even be able to predict and mitigate natural disasters like tsunamis and hurricanes with much greater accuracy.
Okay, listeners, I hope you're ready, because we're about to go full-on abstract math here. We're talking about the Hodge conjecture. And I know it sounds intimidating, but stick with us.
This one deals with shapes in higher dimensions, so dimensions beyond the 3 that we experience in our daily lives. It's kind of mind-blowing. The Hodge conjecture, it basically proposes a way to classify these mind-boggling shapes using tools from different areas of mathematics, like algebra and topology.
Okay, higher dimensions, algebra, topology. I'm starting to feel like I'm back in college and not in a good way.
Right.
Can you give us like a real-world analogy to help us grasp what the Hodge conjecture is trying to do?
Okay, so imagine trying to understand the structure of a skyscraper, but you can only observe its shadow from different angles. Each shadow gives you some information, but none of them fully capture the building's complexity.
Right.
So the Hodge conjecture is like creating a mathematical framework to connect those different shadow representations, allowing us to understand the entire structure, even in dimensions we can't directly visualize.
Okay, that makes more sense. It's like piecing together a puzzle from incomplete clues.
Exactly. And by solving the Hodge conjecture, mathematicians hope to gain a deeper understanding of these higher dimensional spaces, which, who knows, could have implications for fields like theoretical physics and even our understanding of the shape of the universe itself.
Okay, on to the next one. The Birch and Swinnerton-Dyer conjecture. This one, from what I've gathered, has something to do with equations with an infinite number of solutions.
Yeah.
But doesn't that seem kind of paradoxical? Like, how can an equation have infinite solutions?
I know, it seems counterintuitive. But certain types of equations, particularly those dealing with elliptic curves, can actually have an infinite number of solutions. And the Birch and Swinnerton-Dyer conjecture, it offers a way to determine exactly when this happens.
Elliptic curves, didn't those have something to do with cryptography?
You got it. Elliptic curves are actually used in modern cryptography. Their complex mathematical properties make them ideal for creating secure encryption algorithms.
So this conjecture, if we solved it, it could directly impact, like, our cybersecurity.
Absolutely. I mean, it could help us develop even more robust encryption methods, but it could also potentially expose vulnerabilities in existing ones. And the fact that this conjecture is connected to number theory, it makes it a really fascinating puzzle for mathematicians, because it delves into the very nature of numbers and their relationships. Really cool stuff.
All right, last but not least, we've got the Poincare conjecture. And this one's the odd one out, because unlike the others, it's been solved.
Yes. Back in 2003, Grigory Perelman, this brilliant but very reclusive Russian mathematician, provided a proof for the Poincare conjecture.
Okay, so in like super simple terms, what does the Poincare conjecture actually say?
So essentially it states that any three-dimensional shape, as long as it doesn't have any holes, can be continuously transformed into a sphere.
So it's about understanding like the fundamental shape of space itself.
You could say that. It has some pretty significant implications for topology, which is the study of shapes and spaces. But what makes this story even more interesting is that Perelman, he declined both the $1 million prize and the Fields Medal, which is the highest honor in mathematics. He basically chose to withdraw from the mathematical community entirely.
Wow. That's pretty incredible. So there we have it. The 7 Millennium Problems.
Yeah.
Some solved, most still shrouded in mystery. But each one is pushing the boundaries of human knowledge.
And it's not just about finding the solutions, it's also about the process. Just attempting to understand these complex problems, it expands our intellectual horizons, it inspires us to think in new ways, and that's really valuable.
I completely agree. It's mind-blowing to think about the potential breakthroughs that await if even just one more of these problems is cracked. Imagine what secrets of the universe we could unlock.
It really underscores the importance of supporting scientific research and encouraging curiosity and a love of learning.
So, to all our listeners out there, keep those brains buzzing, stay curious, and who knows, maybe someday you'll be the one to add your name to the annals of mathematical history.
You never know.
Thanks for listening, everyone.
See you next time.